In this video, I want us to talk about acids and bases. So we have two theories that we're going to base our definitions on. The Arrhenius theory and the Lowry-Brønsted theory. So under Arrhenius theory, an acid is a substance that produces hydrogen ions, while a base is a substance that produces hydroxide ions. But that's very vague. Let's go ahead and take a look at how that actually looks like. So, Arrhenius theory. An acid produces hydrogen ions. Let me show you what I'm talking about. So, for instance, let's take HCl as an example, and then plus H2O. What are we going to get? We're going to get Cl minus plus H3O plus. This presence of H3O plus is what we refer to as hydronium ions. But the definition says hydrogen ions. So why are we now talking about hydronium ions? Well, they, for the most part, treated the same. Take a look at this. HCl can give us H plus Cl minus. So if a substance produces H3O plus or H plus, then it is considered an acid. It produces hydrogen ions or hydronium ions. So this is how we define an acid under Arrhenius theory. Let's go ahead and take a look at a base once more. So we say that a base is a substance that produces hydroxide ions or OH minus when it dissolves in water. So let's go ahead and take a look at that. So which base can we use? Let's take NaOH. We're going to come across these bases so many times. It is sodium hydroxide. So NaOH, let's dissolve it in water. What are we going to get? We're going to get Na plus OH minus. This is a base. When dissolved in water, it produces hydroxide ions. Do you understand what is going on?
Not really, especially on acids.
Okay, what is the issue there with the acids?
Okay, so it was said that HCl plus H2O give us H3O plus Cl minus, right?
Yeah.
So here he said HCl gives us H plus Cl minus. Does it mean that the H plus that HCl gives is dative covalently bonded to H2O?
Oh, yes. Yeah, that is grade 11 knowledge right there, covalent bond. I forget about that sometimes. Yeah, I think we can say that. We can even go ahead and draw a low structure diagram and see if we're gonna get H3O plus. But I know this to be true. It's just that in grade 12 physical sciences, we don't even think about it. We just know that HCl plus H2O will give you Cl minus plus H3O plus. So these two equations, they're gonna lead to the same consequence all the time. So whether in an exam you decide to use this equation 1 or you decide to use this equation 2, the consequences are going to be the same. That is going to be clearly demonstrated when we solve some problems. Can you take a look at the second definitions? Okay, Lowry-Brønsted theory. This is actually the easier between the two. Arrhenius theory, well, still easy, but Lowry-Brønsted theory is relatively easy compared to Arrhenius theory. So what does Lowry-Brønsted theory say? Let's take a look. An acid is a proton donor and a base is a proton acceptor. That's it. That's the definition. You can come across this in the exam for 2 marks. What is an acid? And then you say proton donor and then you get 2 marks. So 1 word, 1 mark. And then a base is a proton acceptor. Alright. And then obviously, if you talk about the acceptance of a proton and the donation of a proton, then we go ahead and talk about what we refer to as an conjugate acid-base pair. We talk about what we refer to as a conjugate acid-base pair. Okay, but before we can just talk about acid conjugate base pairs, let me just show you what we're talking about when we say that an acid is a proton donor and a base is a proton acceptor. Maybe before we can do that, tell me, is H2O an acid or a base?
It is a neutral substance.
Okay, right. Most of the time, if it is reacting with an acid, it is going to act as a base, and then if it is reacting with the base, it's going to act as an acid. And we can show this idea of an acid being a proton donor and a base being a proton acceptor clearly using a reaction between an acid and the H2O, a reaction between a base and H2O, and even just a reaction between a common acid and a base. We can still demonstrate that fully well. So let me show you what I'm talking about here. Let's say, for instance, we have HCl plus H2O. There we go again, to give us Cl minus plus H3O plus. Okay, so take a look at this definition. An acid is a proton donor. What do we mean by proton donor in our case? H plus. And the base is a proton acceptor, H plus. So take a look at HCl. We start with HCl, and then now we have Cl minus. So what has happened there? From HCl to Cl minus, what has happened there? Well, we had a proton, we had H plus, and now it's no longer there anymore. It would imply that this HCl is an acid because it is a proton donor. It has donated a proton. It was HCl, now it is HCl, it is a Cl minus. Initially it was HCl, now it is Cl minus. So clearly it has donated a proton. So we would refer to it as an acid.
Okay, does it mean that to classify SPs as an acid or a base, we do not consider the hydrogen?
You'd have to explain to me what you mean by that when you say we don't consider the hydrogen. In this example that we have, what is leading you to say we don't consider a hydrogen when we consider a species an acid or a base?
Okay, it is because to consider HCl an acid, we spoke about Cl being negative, and we did not talk about H being positive.
Okay, our definition is that an acid is a proton donor. So the only reason why we're saying that HCl is an acid is because it has donated a proton. Because take a look at this. HCl is made up of H plus and Cl minus. So this is HCl, right? And then after it reacts with H2O, we now have Cl minus plus H3O plus. So it has donated a proton. That's why we're referring to it as an acid.
Okay.
Okay, so let's get rid of this. So HCl in this case is our acid. Okay, and then if this is an acid, then the H2O will act as a base. But is it clear that it's a base without putting that into context? What is a base? A base is a proton acceptor. So tell me, does H2O accept a proton?
Yes.
Yeah, it accepts a proton to become H3O plus. So because it accepts a proton, we refer to it as a base. That's it. That is Lord Brønsted theory. So HCl is an acid because it donates a proton, and H2O in this case will be a base because it accepts a proton. Right. So that is acid, that is base. We're about to talk about conjugate base pairs in a few, but let me just give you another example of a reaction between an acid and a base. Right, so instead of using H2O, let's just go ahead and use NH3 plus H2O. So NH3 is a common base, and H2O in this case will act as an acid. But what are we going to have ultimately? We're going to have NH4 plus OH minus. So let's go ahead and break this down. Take a look at NH3. Is NH3 acting as an acid or a base in this situation?
it is acting as a base.
Why do you say that it is acting as a base?
That is because here it accepted a proton.
And then H2O on the other end?
It is acting as an acid.
And why is that so?
Because if we have a base here, H2O will act as an acid, and it has also donated a proton.
Right. Okay, so we say that this is a base because it accepts a proton, and then this is an acid because it donates a proton. Right. Okay, so if this reaction was reversible, so we're taking a look at it from the product side going to the reactants. What would you classify OH as?
I would classify it as a base because according to Arrhenius theory, it says that bases are substance which produces hydroxide ions.
Okay, right. That is according to Arrhenius theory. If you were to classify it as a base and have to explain according to Lowry-Brønsted theory, what would you say in that case?
I would say that OH minus is a base, and that is because according to Brønsted-Lowry, a base is a proton acceptor. Ooh.
Yes, that's true.
This one,
Yeah.
clearly, we have OH minus, which has become H2O, meaning that it has accepted a proton, and NH4 will become NH3, losing a proton.
Okay, so OH minus is our base, and NH4 is what?
It's an acid.
When we break down a reaction in this way, this is what we refer to as an acid-base conjugate pair. This is an acid-base conjugate pair. Right, so if a question says identify a conjugate acid-base pair in the reaction above or in the reaction below, this is what you need to do. By definition, an acid-base pair consists of two species in an acid-base reaction. One acid and one base that differ by the loss of or a gain of proton. Right, so the difference between these base, let me change my color here. The difference between these base and this acid is a loss of a proton or a gain of a proton, depending on how you look at it. And then the difference between H2O and OH minus, still the same, is a loss or a gain of a proton, depending on how you look at it. So this is an acid-base conjugate pair. Right, so we've touched on the Arrhenius theory, we've touched on Lowry-Brønsted theory, and we've touched on conjugate acid-base pairs. Now, let's take a look at an amphiprotic species. So it is a species that can act as either an acid or a base. A species that can act as either an acid or a base. A good example of an amphiprotic species, we used to call it an ampholyte back in the days, is H2O. Clearly, you've seen that when H2O reacts with a base, it acts as an acid. And then when it reacts with an acid, it acts as a base. So it is amphiprotic because of that. It can act as either an acid or a base. H2O is not the only species that can act as either an acid or a base. We'll see that as we progress. We're going to come across examples where we have an amphiprotic species, or we're supposed to identify an ampholyte and it's not H2O. So for the time being, just remember that an amphiprotic species is a species that can act as either an acid or a base. But anyway, stories, let's go ahead and take a look at the following concept. Different acids and different bases have different strength and so on. That is our next aspect. That is what I want us to touch on. So we'll talk about strength of weak and strong acids, dilute and concentrated solutions, and Ka and Kb values. Ka and Kb values derived from Kc, right? Chemical equilibrium. and then acid-base reactions and neutralization reactions. Right, so let's go ahead and take a look at it. A weak acid or base is one where only a small percentage of molecules will dissociate to form ions in a solution. A weak acid or a base is one where a small percentage of molecules will dissociate to form ions in a solution. Right, so weak acids ionize incompletely in water to form a low concentration of H3O+, while weak bases dissociate or ionize incompletely to form a low concentration of OH-. So if a base or an acid produces a low concentration of H3O+ or OH-, then it is considered weak. An example of a weak acid is hydrofluoric acid, HF, of which when it ionizes, it produces a low concentration of H3O+. We can see that denoted by the arrow here, that in the forward reaction, not much products are formed. Right, it produces a low concentration of H3O+. An example of a weak base is magnesium hydroxide, which only dissociates partially into Mg2+ and OH ions. Let's talk about this Ka value and Kb value that is derived from chemical equilibrium. So Ka will always take the products if they are aqueous or gases, no liquids or solids. So Ka in this case will be H3O+, and then multiplied by the concentration of F minus, everything divided by the concentration of HF. Obviously, we're not going to include H2O because it is a liquid. In these expressions, we only consider gases and aqueous solutions. So let's take a look. Ka. So we're saying that this is a weak acid. So the Ka value, we expect it to be less than 1 in weak acids. So in weak acids, the Ka value is less than 1. For HCl, for instance, which we know to be a strong acid, the Ka value would be greater than 1. Why will the Ka value be greater than 1? Because our denominator will be greater than our numerator because it produces a higher concentration of H3O+, right? Here we have Ka being less than 1 because it is a weak acid. We're gonna have a proper fraction. If we have a proper fraction, it is a weak acid. But then if we have an improper fraction, then it is a strong acid. Our Ka value will be greater than 1. So this is for strong acids, right? And then we can also derive almost the same for bases. We have what we call the Kb value for bases. So it is the ionization or dissociation constant, of which still the same thing applies. If Kb is less than 1, then we have a weak base. And then if Kb is greater than 1, then we have a strong base, not a weak, but a strong base. We have a strong base, right? And then whether it is greater than 1 or less than 1, it is going to be decided by the concentration of OH-, right? So this is weak and strong bases. If you have a strong acid and you want to use it, most of the time you have to dilute it first just to weaken it a bit because it is too corrosive to use in its original state. So let's touch on diluted and concentrated. It is clearly depicted in this picture. Take a look at concentrated and take a look at dilute. When you take a look at dilute, you can see that we have a few molecules of whatever substance we have there, and then in concentrated, well, it is concentrated. Let's take a look at the definitions. A concentrated solution is one where there is a high ratio of dissolved substance, right, solute to solvent. And then dilute solution is one where there is a low ratio of dissolved substance to solvent, right? So that is concentrated and dilute. This is what we are essentially saying. An acid is strong if there is a high percentage of ions formed in the solution. And a base is strong if there is a high percentage of ions in the solution. An acid is going to be H plus and the base is going to be OH minus. And then a weak acid, only a small percentage of ions are formed in the solution, while a weak base is the same, right? Just different ions. In acid, we know that it is H plus, and then in bases, it is OH minus. Now let's talk about concentrated and dilute. Concentrated, large number of molecules of acid in a solution, while dilute, we have a small number of molecules in a solution. And then the base, well, quite the same, large number of molecules in a base solution, and then a small number of molecules of base in the solution, that is dilute. So we have talked about the strength, and we've talked about concentrated and dilute. What we're about to touch on now is what acids and bases is all about. You'll come across a question in the exam, 8 marks, 9 marks, in some cases even 10 marks, requiring all the things we are about to talk about now. So when an acid and a base react, they form a salt. There's something cool that we're going to talk about with regards to that. If the base contains hydroxide ions, then water will also be formed. The word salt is just a general term which applies to the products of all acids and base reactions. A salt is a product that is made up of the cation from a base and an anion from an acid. Cation, just positive ion, and anion is a negative ion. Right. A salt is a neutral ionic compound composed of cations and anions. It is the result of acid-base neutralization reaction. Right, so we know that when you have an acid and a base, one of the products that you're going to have is salt, right? Stories. And then when an equivalent amount of acid and base react, so that neither the acid nor the base are in excess, the reaction is said to have reached the equivalence point. At this point, neutralization has been achieved. So if we have equal amounts of acids and base, and then they react completely, and there's no base or acid in excess, we say that we have reached a equivalent point, right? And then that is where we can say neutralization has been achieved. Right, just to touch on this, if you have ulcers, your stomach produces too much acid, and the medication you take is just a base that goes and neutralizes that acid, and then you're just left with salt in your stomach and not the acid anymore. So these acid-base reactions, they're very key to a lot of medication that you take, to a lot of household uses. Right. And then equivalence point, let's take a look at the technical definition. When a stoichiometrically equivalent number of moles of both reactants has been added to the reaction. If the base contains hydroxide ions, then water will also be formed. Right? You've seen from the reactions we have covered up to so far that most of the time water is one of the products, or is one of the reactants. And there is something profound about H2O that I want us to take a look at. Take a look at this reaction between H2O and H2O. We literally have H2O plus H2O. So what's going to happen? One H2O will act as an acid and the other one will act as a base. And then consequently, we have H3O plus and OH minus. Right. H2O plus H2O to give us H3O plus OH minus. This is what we call autoprotolysis. It's the transfer of a proton between two of the same molecules. Right, we have a transfer of a proton here between H2 and H2O essentially. But what is the consequence of this? It leads us to the auto-ionization of water. Well, this is what we're talking about here. It's the reaction of water with itself to form H3O plus ions and OH minus ions. What is the equilibrium constant for the auto-ionization of water, or what we refer to as Kw? Oh, well, clearly you can see that it is equals to H3O plus multiplied by OH minus, right? These are our products. And then for the reactants, we're not going to have anything because we have H2O and H2O, which are in liquid phase. And like I've said, we only consider aqueous solutions and gases, right? There's quite a difference between liquid and aqueous, which a lot of people don't realize, right? So H3O plus multiplied by OH minus, this gives us 1 times 10 to the minus 14, right? This is the equilibrium constant for the auto-ionization of water. This right here is very consequential. We're going to use this time after time. We are going to derive a lot of things from this concept. H3O plus multiplied by OH minus, it's 1 times 10 to the power minus 14. Well, from this, we can actually get to showing that pH is equals to 14 from this. This is where a lot of things stem from, right? You'll see that in a few. But for the time being, let's take a look at how we can use that to calculate ion concentration, right? Although you normally ignore the auto-ionization of water in calculating the H3O plus concentration in a solution of the strong acid, the auto-ionization equilibrium still exists, and it is responsible for a small concentration of OH minus ion, right? Let's take a look at example. Calculate the concentration on OH minus ion in 0.1 mole per decimeter cube. Well, you can see that this question doesn't make much sense. I think there's a typing error here. So let's take a look at example 2 instead. The concentration of a solution of NaOH, a strong base, is 0.01 mole per decimeter cube. Calculate the OH minus and H3O plus concentration in this reaction. Okay, let's go ahead and take a look at that. So we have NaOH, and we're supposed to calculate the concentration of OH minus and H3O plus. So how can we possibly do that? We know that NaOH associates or dissociates to form Na plus OH minus. We know this to be true, right? So NaOH minus and OH minus, well, they are in the same, they have the same volume, right? Because we are getting this OH minus from the NaOH, right? They're not reacting with anything else that would increase or decrease the volume. Even if that was the case, they would still be in the same container, so to say. So the volume would be the same. So the volume is the same, right? Is the number of moles, are the number of moles going to be the same? Well, the balancing coefficient of NaOH and OH minus is 1. So the number of moles are going to be the same also, right? So the volume is the same, the number of moles are the same, right? So are the concentrations going to be the same? Yes, they should be, because concentration is just number of moles divided by the volume. So what is the concentration of NaOH? The concentration of NaOH is 0.01 moles per decimeter cube. So the concentration of OH minus should also be equals to 0.01 moles per decimeter cube, right? So we have the concentration of OH minus, but using this concentration of OH minus, can we find the concentration of H3O plus using the concentration of OH minus? Yes, we can, using the auto-ionization of water. That's why I was saying that that concept is very consequential in what we are going to be doing. Take a look at this. So OH minus multiplied by H3O plus, we had said that this is equals to 1 times 10 to the minus 14. Well, it should be easy to see what we are going to do here. The concentration of H3O plus is going to be equals to 1 times 10 to the minus 14 divided by the concentration of OH minus, which is 0.01. Well, do I need to put that in my calculator, or I can just do it in my head? I think I can. So H3O plus is going to be equals to, let's take a look, 1 times 10 to the minus 12 moles per decimeter cube. Well, let me just verify that. So we have 1 times 10 to the minus 14 divided by 0.01. Right, I think we are good to go. So that is how you can calculate the concentration of H3O plus if you have the concentration of OH minus. This is not something that is optional. You are going to use this at some point of time. There is no way you're not going to use it. So yeah, it is better if you familiarize yourself with this concept. So right, I've said that the auto-ionization of water is what leads to the pH value, well, the max on the pH scale being 14. So let's go ahead and take a look at pH scale. Right. A secondary way of expressing hydrogen ion concentration, avoiding using very small number of exponential notation, is the pH scale. So right, the pH scale is just there to express the concentration of hydronium ion without using smaller number. Right, pH is used to measure the concentration of H plus and therefore whether a substance is acidic or basic. Solutions with the pH less than 7 are acidic, while those with the pH greater than 7 are basic. The pH scale ranges from 0 to 14, and a pH of 7 is considered neutral. See the figure below. Well, there's no figure to see here, but yeah, that's the pH. We are ranging from 0 to 14. Less than 7, it's an acid, and greater than that is a base. Nothing new there. We've been talking about that since grade 9. pH is used to measure the concentration of H plus, but in such a way that doesn't include using very small numbers, right? So pH, the formula for pH is equals to minus log of H plus, right? You can see here that the only input we have is the concentration of H plus. So the only thing that is affecting the value of pH is H plus and nothing more. And then this log here is what ensures that we don't have very smaller numbers, because if we just said pH is equal to H plus, we would still have consistency, right? We would still have consistency. We wouldn't have any issue per se, but then we use log so that those small concentrations can be presented or represented in digestible numbers, right? We don't have to use 1 times 10 to the minus 12, because think about what 1 times 10 to the minus 12 means. It means 0.0000011 zeros until 1. That is very strenuous. So instead of doing that, we introduce log, right? And then we get numbers from 0 to 14, and that is easy to work with. So pH is equals to minus log of H plus. But pH is not the only thing that we talk about here. We also talk about pOH. So this is how we measure the concentration of OH minus therefore. So pOH, as you've guessed, will be minus log of OH minus. So this is pH and this is pOH. Remember that we said H plus multiplied by OH minus is equals to 1 times 10 to the minus 14. Okay, let's introduce log on both sides. I want to show you something very cool. So if we were to introduce log on both sides, we would have log of H plus multiplied by OH minus, right? We can, if what you do on the left, we must also do it on the right. So here we're going to have log of 1 times 10 to the minus 14, right? But log of A multiplied by B is equals to log of A plus log of B. That is a log law, right? So what are we saying? We're saying that we're going to have log of H plus log of OH minus. We have applied a log law there. And then log of A to the power B is equals to B log of A. So A, well, let me not use B. B in our case is minus 14. We're going to have minus 14 log of 10. Right. But we know that log of 10 is 1. So let's just replace this with 1. 1 times minus 14 is just going to give us minus 14. If we divide both sides by minus 1, we're going to get... If we divide both sides by minus 1, we're going to get minus log of H plus minus log of OH minus being equals to 14. But what is minus log of H plus? This is pH. And then minus log of OH minus, this is POH. And all of this is equals to 14. So there we go. pH plus POH is equals to 14. We are also going to use this concept at some point of time. Okay, let's solve some problems. Calculate the pH of a solution where the concentration of hydronium ions is 1 times 10 to the minus 3 moles per decimeter cube. So what is hydronium ions? Hydronium ions is H3O plus. And I've said that in place of H plus, we can always use OH, not OH, but H3O plus. Right, so if you're given the concentration of H3O plus, you just treat it as H plus. Right, so here we're supposed to calculate the pH. There isn't much to do. It's just direct substitution, really. So we're going to have pH being equals to minus log of H3O plus. Right, we can use H3O plus and H plus interchangeably. This is going to be equals to minus log of 1 times 10 to the minus 3. Right, so let me just go ahead and put that in my calculator. So minus log of 1 times 10 to the minus 3 is equals to 3. So the pH in this case would be equals to 3. If the concentration of hydronium ions is 1 times 10 to the minus 3 moles per decimeter cube. Well, the pH is equals to 3. It's easy to see that the POH should be equals to 11. Because the pH and the POH, if you say pH plus POH, you get 14. So if pH is 3, then POH should be 11. We can easily prove that, but stories. I'm sure we're going to have a question where we're going to have to do that as time goes. Example 4. In a 162 centimeter cube solution of ethanoic acid, the following equilibrium is established. We are given an equation here, and then the question says the number of moles of CH3COO minus is found to be 0.001 moles. Calculate the pH of the solution.
So we've been given the number of moles of CH3COO minus, and it has been given as 0.001 mole. So the balancing coefficient of CH3COO minus is the same as the balancing coefficient of H3O plus. And the balancing coefficient of H3O plus is the same as that of ethanoic acid. So the number of moles of H3O plus and the number of moles of ethanoic acid is equal. We've been given the volume of the ethanoic acid as 162 centimeter cubed. But using the formula of C equals to N over V, the volume of ethanoic acid should be in decimeter cubed, not centimeter cube. To convert centimeter cube into decimeter cube, we will have to divide 162 by 1000, which will give us 0.162. Therefore, the volume of H3O plus will be 0.162 decimeter cubed. So to calculate the concentration of this H3O plus, we will have to divide the number of moles, which is 0,001, by the volume, which is 0,162. And that will give us 0,006. 0,006 moles per decimeter cubed. So the formula of pH is equals to negative log of H3O plus, which can also be H plus. pH will be equal to negative log of 0,006, which will give us 2,22.
It is as if every time we touch a different aspect, I keep on saying, oh, this is very important, we're going to use it at some point of time. And I just have to say it again, titrations of acids and bases. This is very key. We are going to use this time after time. I think you're even going to do a practical on this, acid and base reactions. Or you should do it at some point of time in your high school years, either grade 11 or 12. But yeah, it's very rare that you're going to finish high school without doing titrations. Yeah, this is very important. So let's take a look and see what is really happening here. The neutralization reaction between an acid and a base can be very useful, as we have talked about previously. If an acidic solution of known concentration is added to a basic solution of unknown concentration until the solution is exactly neutralized, it is possible to calculate the exact concentration of the unknown solution. Right. So that is what titration is all about. We are using the concentration and volume of a known substance to calculate the concentration and volume of the unknown. Right. Titration is a technique where a solution of known concentration is used to determine the concentration of an unknown solution. This process involves the gradual neutralization reaction of an acid by a base or of a base by an acid. Right. So if you're given an acid with known properties, you can find the properties of an unknown base. And then if you're given the properties of a base, then you can find the properties of an acid that are unknown at that point using this reaction. Right. Titration is a method used to determine the concentration of a known substance using another standard solution. So what is a standard solution? A standard solution is a solution of known concentration. Okay. The titration of an acid in a aqueous solution with a base is illustrated in the series of photographs below. Right. The titration of an acid in a aqueous solution with a base. Okay. So let's take a look at this. It is a titration of an acid with a base. Okay, so here in our beaker, we have our acid, right? And then here in our burette, we have our base, right? So we don't know the properties of this acid, right? But we know the properties of a base. So what are we going to do? We keep pouring a bit of base in our acid. Just a bit, right? We have an indicator here in our acid. We have put an indicator inside it. And then when the color of the indicator changes, well, different indicators change color when the reaction has reached an equivalence point. So when the color of the indicator changes, we know that we have stoichiometrically equal number of moles of acid and a base. We know that neutralization has occurred. So because we know the amount of acid that we have poured in, we can then determine the amount of acid that should have been in the beaker to begin with. That is what titration helps us with, right? So we have an acid of unknown properties, and we keep pouring a small amount of base until the indicator changes color. When the indicator changes color, we know that neutralization has been reached. We are at the end of our reaction now, and using that information we have with regards to the base, we can then determine the properties of an acid. So this is essentially what titration is all about. But which indicator do we use and when do we use it? Because we have a couple of indicators. Let's talk about that. An indicator is used to determine the endpoint of neutralization. Okay, let's go ahead and take a look. We have three indicators: methyl orange, bromothymol blue, and phenolphthalein. Alright, those are our three indicators. So if you're expecting your endpoint, the endpoint of neutralization, to be reached when the pH is between 3 and 4.4, then you use methyl orange. And then if you expect your reaction, the point of neutralization to be reached when the pH is around 7, you use bromothymol blue. And then if you expect your pH to be around 8, around 10, when the point of neutralization has been reached, then you use phenolphthalein. So how do you know that the pH at which the endpoint of the neutralization is going to be reached is going to be around 3, and you use methyl orange, around 7, and you use bromothymol blue, around 8, and then you use phenolphthalein? How do you know all that? If we have a strong base and a strong acid, then we would expect the pH to be around 7 at the end of our neutralization reaction. In this case, we would then use bromothymol blue. And then if we have a weak acid and a strong base, you expect the pH to be greater than 7, around 8, around 9, around 10, even around 11. And then the suitable indicator in this case would be phenolphthalein. And then if you have a strong acid and a weak base, you expect the pH to be less than 7, right? And then in this case, we would use methyl orange. So there we go. This is how you can have an idea of which indicator you need to use based on the strength of the acid and the base you have at hand. Let's solve some problems. So what we have in front of us is acids and base topic test. So I will do the test myself. That will be the first try. And after doing the test myself, then you are gonna do the test. You can ask questions, I can help you out and so on. But I want to do the test first myself. So let's go ahead and take a look at it. If I'm doing something and then you don't understand where it is coming from, then you can ask me. Right. So question 1. We usually don't read these instructions. We just know what to do, but let's take a look and see what is happening. 4 options are provided as possible answers to the following questions. Each question has only one correct answer. Choose the answer and write only the letter A to D next to the question numbered 1 to 1.1 to 1.5 in the answer book, right? And then, for example, we have 6 with an answer being E, right? 1.1, consider the following chemical reaction. Let's take a look at that chemical reaction. Which one of the following correctly identifies the order of Lowry-Brønsted acids and bases in the above reaction? Okay, so let's take a look at that. What do we have? We have HCO3 minus plus HC2O4 minus, giving us and getting H2CO3 plus C2O4 to the 2 minus. So let's go ahead and dissect this. Okay, so we start with HCO3 to the minus. So if this is an acid, in the product side we must get CO3 2 minus. It would have donated a proton and we would therefore refer to it as an acid. That is if and only if it is an acid, right? So let's go and check and see if that is actually the case. So let's take a look. We start with, let me just erase this. We start with HCO3 minus, and then we end up with H2CO3. So it is not an acid. because it is not donating a proton. It actually looks like it has accepted a proton. It was HCO3 minus, now it is H2CO3. Right, so clearly it has accepted a proton. So if it is a proton acceptor, then this is our base because it has accepted a proton, and then this is going to be a conjugate acid, right? That is going to be a conjugate acid. And in doing that, I think we have for the most part answered our question, because if that is the base, then this is the acid where we are getting the proton from, and then this is going to be the conjugate base. So there we go. Our order, we have base, acid, acid, base. So let's go ahead and look at our question and see which option is that. So okay, B and C, well, B and D starts with a base, followed by an acid, right? It's still true in both B and D. And then the third, what fills the third spot is acid, right? So that is option B. So option B seems to be the correct answer here. We have base, acid, acid, base. So there we go. You essentially, for the most part, you just need to identify one acid. As soon as you identify one acid, everything else, it's easy to figure out, because if you have an acid, then it's the reaction with the base, and then the conjugate acid and the conjugate base. But anyway, stories, that is 1.1. So for 1.1, the answer is B. What about 1.2? Let's go ahead and take a look at that. Which of the following species cannot act as a Brønsted-Lowry acid? And cannot, right? Cannot. I was thinking can, right? Cannot act as a Brønsted-Lowry acid and as a Brønsted-Lowry base. So we are looking for a species which is not an amphilite, amphiprotic. We are looking for a species which cannot act as a base and act as an acid. We know H2O. We know fully well that H2O is an amphilite. It can act as both an acid and a base. So option B cannot be our answer, because we are looking for a species which cannot. And then HSO4 minus can act as both an acid and a base. Well, let me show you how it can act as an acid. So let's say we have HSO4 minus plus H2O. This can give us SO4 2 minus plus H3O plus. As you can clearly see here, it is acting as an acid because it donates a proton. But H2SO4 plus H2O gives you HSO4 minus plus H3O plus. Clearly here we have H2SO4 as our acid and HSO4 minus as our conjugate base. So in the first reaction it is acting as an acid, and then in the second reaction it is acting as a base. So clearly this is an amphilite. It cannot be our answer to 1.2. It acts as both an acid and a base. And we can do the same for D, right? D will also act as an acid and as a base. That is if we are really sticking to the basics. But we know that A is ethanoic acid. A is ethanoic acid. It is an acid. It doesn't act as a base. A is ethanoic acid. So the answer here in 1.2 is A, right? Whether you are getting to that answer because you know fully well that A is an ethanoic acid, or you just use this concept, you just dissolve the compound in water and see what you end up with, right? So that is 1.2. 1.3, the compound which will react with sodium hydroxide in a neutralization reaction is. So right, a neutralization reaction is a reaction between an acid and a base. So essentially what the question is asking us here is, between A, B, C and D, which one is an acid? Because if we have a base and an acid, we have a neutralization reaction. So take a look at this. We have NaOH as our base, that is sodium hydroxide, and then option A is KOH. KOH is potassium hydroxide. This is also another strong base, so we cannot have base plus base and call that neutralization. No, we need a base and an acid. So this can't be our answer. And then we have CaCO3. This is the compound you find in shells, right? And then it is basic. CaCO3 is basic. So CaCO3 and NaOH, they also can't form a neutralization reaction because they are two bases, right? So B cannot be our answer. And then C2O4 to the 2 minus. This is not a very usual compound, well, ion in this case, that we come across. So maybe this one can be a bit confusing. But if we just take a look at question 1.1, because we're not sure whether C2O4 to the 2 minus is an acid or base, right? Let's say it's not easy to see, but we can actually use 1.1 and see that C2O4 to the 2 minus is a base, as you can clearly see here. When we were identifying our conjugate acid base pair, we say that C2O4 to the 2 minus is a base. So this cannot be a neutralization reaction between a base and a base. 1.3, we have ethanoic acid. So this is our answer. The answer to question 1.3 is A. Not A, but D. It's D. It is ethanoic acid because we have a base in NaOH and then we have an acid in CH3COOH. So clearly, this is going to be a neutralization reaction because it is a reaction between an acid and a base. Right, that is 1.3. Let's take a look at 1.4. 1.4, when sulfuric acid reacts with water, it ionizes in 2 steps, as shown in the 2 balance equations below. Well, there's a special term we use for acids that ionizes in 2 or 3 steps, right? So sulfuric acid, it says H2, so it is diprotic. It can donate 2 protons. In reaction 1, it donates the first proton, and then in reaction 2, it donates the second protons. While HCl is monoprotic because it can only donate 1 proton, right? So that is another concept that we brushed over when we were touching on the basics. So right, back to the question. 2 steps of which sulfuric acid ionizes. And then what is the question saying? The species are represented by letters Q and R. Okay, let's take a look. So reaction 1, we have H2SO4 plus H2O to give us H3O plus what we are referring to as Q. Well, let's put it here, what we are referring to as Q. So how can we possibly identify Q? We know that there is no element that is just going to disappear in our reaction. Everything needs to be accounted for. So take a look at this. We start with H2O. Now we have H3O plus. So clearly H2O has gained a proton. But where is the proton coming from? It's coming from H2SO4. There is no other species. That should be easy to deduce that the proton is coming from H2SO4. But when H2SO4 donates the proton, what are we going to be left with? We're going to be left with 1 proton, 1 hydrogen, right? And then SO4 minus, because we have donated 1 proton, and then here it is plus because it has accepted 1 proton. So we know that Q is HSO4 minus, right? So at this point we know that A cannot be our answer because it says Q is SO4 to the 2 minus. And then we know that, let's take a look, HSO4 minus, we know that D cannot be our answer because D says that Q is HSO4 to the 2 minus, and Q is clearly HSO4 to the minus 1, not to the 2 minus, right? So we have figured out what Q is. Let's go ahead and do the same for R. So for R, we're starting with Q. What is Q? Q is HSO4 minus. There we go. And then plus H2O. And then what is the product? The product is H3O plus R. Okay, so let's take a look. Back to the basics again. We will start with H2O Now we have H3O plus. It has accepted a proton. Where is the proton coming from? The proton is coming from HSO4 minus. So when it donates another proton, and well, let me not say another proton, because now we are in a different reaction here. When it donates a proton, we're going to be left with SO4 2 minus. So this is Q and this is R. The answer to 1.4 is C, and let's do 1.5. Right. So 1.5. Let's take a look at what's happening here. Consider the incomplete chemical equation below. There we go. Looks a bit complicated, but there ain't nothing to it but to do it. Which one of the following is represented by X in the above equation? So I think here we're just following the same technique we've been trying to, well, we've been using to answer 1.4 and 1.5 and 1.1. So let's take a look. We have some X plus 2HNO3 to give us CaOH2 or OH, no, NO3, right? NO3 2 plus H2O plus CO2. Right. I think this is quite easy. It is easier than it looks because we can just use brute force here. Let me show you what I'm talking about. So, okay, the hydrogens. Let me just change my color. So we have 2 hydrogens on the left. On the right, we have 2 hydrogens. Okay, all is well there. Okay, let's do nitrogen. In nitrogen, we have 2 atoms of nitrogen, right? And then in the right, that's on the left hand side. And then on the right hand side, the same is true. We have N2. So there's no issues with regards to nitrogen. They are balanced. What we have on the left is what we have on the right. And then oxygen, we have 2 multiplied by O3. So this is O6 on the left. And then on the right hand side, we have O3 multiplied by 2. This is O6. And then this oxygen from H2O, which will make that O7. And then on CO2, we have 2 oxygen atoms. So this will give us a total of O9. So we can see that issues are arising at this point. 6 oxygens on the left, 9 on the right. So we know that in X, some way, somehow, we need to have an oxygen. Right? We know that for sure. We're just following the basics. What's on the left must be on the right. Okay, so that is with regards to oxygen. And then when we move to the right hand side, we have calcium on the right hand side, and then on the left hand side we have no calcium. So we know that at least we need Ca as part of X some way, somehow, right? We don't know how it will look like, but we know that we at least need calcium on the left, right? So that is Ca. And what else do we have? I think we've covered hydrogen and all is well. We need carbon. On the right hand side, we have a carbon, and then on the left, we don't have a carbon. So it is easy to see that we also need a carbon on the left hand side. So we have calcium, we have oxygen, and we have carbon. Okay, how many calciums do we have on the right? We have 1. How many oxygen do we have? Well, let's start with carbon. How many carbons do we have on the right? We have 1. How many do we need on the left? We need 1, obviously. And then let's come to oxygen. On the right, we have 9 oxygens. And then on the left, we have 6. The difference is 3. So here we need 3 oxygen. So on the left, in place of X, we have CaCO3. So the answer to 1.5 is D. We are using brute force here. Even if you don't have an idea of what chemistry is all about, even if you just look at the mathematical, if you just solve this problem basing it on math, we should end up with CaCO3. So the answer to 1.5 is D. Let's do question 2. So question 2, consider the following acid-base reaction. And then 2.1.1, define an acid in terms of the Lowry-Brønsted theory. Also, the Lowry-Brønsted theory is the easy one. So an acid is a proton donor. Right, so proton donor, and then we have 2 marks. Yeah, 1 mark for one word. Okay, that is 2.1.1. Then 2.1.2, write down the formula of the 2 acids in the above reaction. Well, we are back to acids base conjugate pairs. Let's go ahead and do that one more time. HCO3 minus plus NH3 to give us CO3 2 minus plus NH4 plus. Right, so we have done 2.1.1. We've already defined what an acid is according to the Lowry-Brønsted theory. Now we need to write down the formula of 2 acids in the above reaction. Okay, so let's take a look. HCO3 minus. It doesn't really matter what you start with. You can start with anything, really. Let's start with NH3. Right, so NH3. If it is an acid, we should have NH2 minus. It has donated a proton. And then if it is a base, we should have NH4 plus. It has accepted a proton. So let's take a look. We have NH3 and then we end up with NH4 plus. So clearly NH3 accepts a proton. If it accepts a proton, it is a base. So this is a base, right? And then we are done essentially. If that is the base, this is its conjugate acid. This is gonna be a base, and then this is the conjugate acid. So the formula of 2 acids in the above reaction. Well, HCO3 minus. It donates a proton to become CO3 to the 2 minus. Which other acid do we have? We have NH4 plus. It is a conjugate acid to the base NH3. So the answer to 2.1.2, HCO3 minus and NH4 plus. Right. 2.1.3, define the term ampholyte. Well, an ampholyte is a substance that can act as an acid and as a base. Right, it can act as both an acid and a base. So that is 2.1.3. 2.1.4. Right. Write down the write down the formula of an ampholyte in the above reaction. Write down the formula of the ampholyte in the above reaction. So let's go ahead and take a look and see what is happening. So what is our ampholyte? Let's take a look at the reaction that we have. Let me just change my color here. I'm just giving myself some time to think here in changing the color. Right, so we have HCO3. Let's start here. We have HCO3 and NH3. Right, NH3 is a base, and then NH4 plus, it is an acid. We don't have such thing as NH2 minus. We don't have such a thing. So NH2 minus, it does not exist. This is not a thing we have in chemistry. So we know that NH3 cannot act as an acid. It cannot donate and become NH2 minus. So this is out of the way. This is out of the way. We know that this cannot be true. And then CO3 2 minus, that is our base. Well, it cannot donate a proton to become CO3 to the 3 minus because it doesn't have a proton. So this cannot be an ampholyte, right? It is acting as a base in this case. Can it donate a proton? No, it cannot because it doesn't have a proton. And then on the other hand, acid NH4 to NH4 plus. Okay, if it is acting as a base, it needs to then become NH5 to the 2 plus, and this is technically impossible. How can you show that is technically impossible, or how can we reach to that conclusion? Try drawing a Lewis structure diagram for NH5 to the 2 plus and see what you end up with. This is technically impossible, right? So we know that NH4 plus cannot act as a base. HCO3 minus, it is an acid, but it can also act as a base. how can it act as a base? Okay, take a look at this. H2CO3 plus H2O. This can give us H3O plus HCO3 minus. No issues arise whatsoever. So you can see that this is the acid and then this is the conjugate base, right? So in this case it is acting as a base, but in our reaction it is acting as an acid, so it can act as both an acid and a base. So 2.1.4, the answer is HCO3 minus. It can act as both an acid and a base, clearly. And then 2.1.5, write down a balanced chemical equation to show how the ampholyte named in question 2.1.4 above reacts with water, in which water acts as an acid. Okay, let's see. HCO3 minus plus H2O. We are saying that we need water to act as an acid. So water needs to donate the proton, and HCO3 minus needs to therefore accept the proton. Okay, so we would have H2CO3 plus OH minus. Okay, let's take a look at this and see if all is well. Write down a balanced equation to show how the ampholyte named in question 2.1.5 above reacts with water, in which water acts as an acid. If water acts as an acid, it shall donate a proton, and HCO3 minus should accept. When HCO3 minus accepts, it becomes H2CO3. Okay, that is well. And then if H2O donates a proton, it acts as an acid, then it will become OH minus. That is also perfectly fine. So that is the answer to 2.1.5. Okay, let's move to 2.2 and hear the stories. So in 2.2, CO3 to the 2 minus in the above reaction is reacted with 20 centimeter cube of 0.2 mole per decimeter cube of hydrochloric acid, according to the following balance equation. Okay, write down a reason why Cl minus is referred to as a base. Write down a reason why Cl minus is referred to as a base. So take a look at this. We start with HCl, which is hydrochloric acid. It donates a proton, and we are left with Cl minus. Right. When we define a conjugate acid or a conjugate base, we say that it is the ion, it is the space that is left after an acid has donated a proton or after a base has accepted a proton. Okay, so Cl minus is what is left after an acid has donated a proton. It is a conjugate base, so that is why we refer to it as a base. It is what is left after an acid has donated a proton. Okay, that is 2.2.1. Then 2.2.2, calculate the number of moles of hydrochloric acid reacted. That is for 3 marks. Let's take a look and see what is happening here. So it is reacted with CO3 to the 2 minus is reacted with 20 centimeter cube of 0.2 mole per decimeter cube of hydrochloric acid. So we have the volume, we have the concentration, we are looking for the number of moles. We are really sticking to the basics here. Concentration is equals to the number of moles divided by the volume. So what is the concentration? 0.2. And then the number of moles is what we are interested in. And then the volume is 20 centimeter cube. We can just multiply it by 10 to the minus 3 and we have converted it to decimeter cube. Right. So let's cross multiply. Number of moles is equals to 0.2 multiplied by 20 times 10 to the minus 3. So 0.2 multiplied by 20 times 10 to the minus 3, 0.004 moles. So there we go. That is the answer to 2.2.2. There's something really complicated here. Let's do question 3 and see what is going on. So question 3, 2 acid-base reactions are shown in the chemical equation below. Okay, And then 3.1.1, define a base according to Arrhenius theory. Arrhenius theory is the difficult one of the two. And then base is a substance that ionizes or dissociates in water to produce hydroxide ions, right? It is a substance that ionizes or dissociates in water to produce hydroxide ions. So that is 3.1.1. What about 3.1.2? I'm glad you asked. Write down the formula of a conjugate acid of OH minus in reaction 1. Conjugate acid of OH minus in reaction 1. So in coming to the conclusion that Cl minus is a base, well, the reason we say that Cl minus is a base, it is because it is the space that is left after an acid has donated a proton. It is therefore a conjugate base. So here, a conjugate acid of OH minus in reaction 1. Okay, so let's take a look. NH3 becomes NH4 plus. It accepts a proton. And then H2O becomes OH minus. It donates a proton. So a conjugate acid to OH minus is H2O. That OH minus is there because H2O has donated a proton. So that which donates, we know fully well that it is an acid. And then the OH minus, it's a base because it's what is left after an acid has donated a proton. So a conjugated base to OH minus in reaction 1 is H2O. That is 3.1.2, not 3.1.1. That is 3.1.2 H2O. Right. And then now 3.1.3, write down the formula of a conjugate base of HPO4 to the 2 minus in reaction 2. I don't think these questions are difficult per se. I think we are really sticking to the basics here. So let's take a look at conjugate base to HPO4 to the 2 minus. So we have HPO4 to the 2 minus reacting with H2O. H2O accepts a proton. So from H2O to H3O plus, it has clearly accepted a proton. And then HPO4 to the 2 minus donates a proton to become PO4 to the 3 minus. So what can we say about that? PO4 to 3 minus is the conjugate base of HPO4 to the 2 minus because it is what is left after the acid has donated a proton, like we are emphasizing. So the answer to 3.1.3, PO4 to the 3 minus. And why is that so? It is what is left after an acid has donated a proton. Okay, the question that follows. Methyl orange indicator is added to the mixture in reaction 1. Right. Methyl orange indicator is added to the mixture in reaction 1 above at the completion of the reaction. The color change of methyl orange indicator in acidic and basic solutions is shown in the table below. Color in acidic solution, it is red. So if the color turns red, then that solution is acidic. And then color in basic solution is yellow. So if the color turns yellow, then we know that the solution is basic. And then 3.1.4, define the term acid base indicator. Yeah, this is not a very common definition, but an acid base indicator, it is a weak acid or a weak base which color changes as the H plus ion concentration or the OH ion concentration in the solution changes. So a weak acid or a base that will change color if the concentration of H plus changes or if the concentration of OH minus changes. Right, so that is an acid base indicator. It changes color when the concentration of H plus changes or when the concentration of OH minus changes. That is suitable. That is a good definition because we need an acid base indicator to change color when a solution becomes acidic or if a solution becomes basic. So if it changes because the concentration of H plus has changed or because the concentration of OH minus is changed, then that is suitable because it is there for acidic or basic. You just need to know what the color change is going to be if it is acidic, and what color change it is going to be when it is basic. That is 3.1.4. 3.1.5. What is the color of the indicator in the reaction mixture? Give a reason for the answer. So the indicator is added in reaction 1. So let's zoom in reaction 1 and make sense of what is happening here. So let me just erase this. So reaction 1. Well, we know that H2O, if you have an acid, is going to act as a base. And then if you have a base, it is going to act as an acid. So take a look at this. We start with H2O and then we end up with OH minus. So is it acting as a base or is it acting as an acid? Clearly it is acting as an acid because it has donated a proton from H2O to OH minus. So H2O is an acid, right? And then we know that NH3 is a base, right? But then even if you were not aware of that, just looking at how H2O behaves, you should reach the same conclusion that NH3 is a base. So what is the pH of H2O, right? The pH of H2O is 7. So what is deciding whether the solution is acidic or basic is NH3, because we know that the pH of H2O is 7. So if you have a base, then the pH will be greater than 7. And then if you have an acid, the pH is going to be less than 7, and then then H2O will therefore act as a base in that case. So clearly here, because H2 is acting as an acid and we have NH3 as a base, then at the end of the reaction, our mixture is going to be basic. So what is the color of the indicator in the reaction mixture? It should turn yellow here, because it is said that the color in basic solution is yellow. And we have H2O, which the pH is 7, NH3, of which the pH is greater than 7 because it is a base. So the answer to 3.1.5, we have yellow. Give a reason for the answer. Well, the reason is because the solution is going to be basic at the end, right? You can also see that by the presence of OH minus. OH minus is hydroxide ions. We know that hydroxide ions is what you get when a base ionizes or dissociates. You get OH minus, right? Okay, and then 3.2. Let's take a look. Let's see what is happening here. 3.2. Write down a balance equation for the dissolution of ethanoic acid. Right. I'm not sure if this is the correct term where we're supposed to use dissociation, but okay. CH3COOH in water. Let's go ahead and take a look. So CH3COOH plus H2O. We know fully well that this is ethanoic acid. So because it is an acid, it should donate a proton. And then H2O must act as a base. It must accept that proton. So the products that we're going to have CH3COO minus plus H3O plus. The acid has donated a proton to become CH3COO minus, and then H2O, which is acting as a base in our case, has accepted a proton to become H3O plus. So that is ethanoic acid in water. It will produce hydronium ions. We expect an acid to produce hydronium ions when dissolved in water. That is 3.2. Question 4. Looks like things are starting to get a bit interesting here, but we are here for that. 4.1. The Brønsted-Lowry and Arrhenius theory are used to define acids and bases. We know that by now. And then 4.1.1. Define a base according to Brønsted-Lowry theory. Define a base according to Lowry-Brønsted theory. Lowry-Brønsted is the easy one. So base is a proton acceptor. Right, so that is 4.1.1. We shouldn't be getting that wrong. A base is a proton acceptor. Okay, 4.1.2. We're given a couple of reactions here, right? And then the question is saying the reaction that illustrates Arrhenius theory. Okay, between A B, and C. So Arrhenius theory says that a substance that produces, it says that an acid will produce hydronium ions or hydrogen ions when dissolved in water, right? And then a base will produce hydroxide ions. So we are looking for that. Which equation produces hydronium ions, or which equation produces hydroxide ions? Let's take a look at equation A. In equation A, we don't have hydrogen ions, hydronium ions, or hydroxide ions. So that is not a good illustration of Arrhenius theory. Reaction B, same is true. We don't have a hydrogen ion, we don't have a hydroxide ions, we don't have a hydronium ions. Not a good illustration of the Arrhenius theory. But equation C, you can clearly see, well, not equation C, but reaction C, you can clearly see that there is hydrogen ion produced, there is H plus, when HCO4 minus ionizes. So the answer to 4.1.2 is C, because clearly an acid is producing hydrogen ions, and that is what Arrhenius theory says. It defines an acid as a substance that produces hydrogen ions when dissolved in water. Okay, 4.1.2. 4.1.3, a substance that can act as an ampholyte. A substance that can act as an ampholyte. From the reactions A, B, and C right down there, substance that can act as an ampholyte. Do we have H2O as one of the reactions here? It's one of the reactions, because if I have H2O, I'm just jumping straight to H2O and then I call it a day. Okay, I do have H2O in reaction A. Well, in reaction A, it is just acting. It's a product there in reaction A. So let's see, do we have any other equation with H2O? We don't have any other reaction with H2O. So whether it is acting as an acid or as a base in reaction 1 is not really gonna matter, because we don't have an opportunity to demonstrate that it is acting as the other in another reaction. Okay, but I'm realizing here that in reaction B we have HSO4 minus, and then in reaction C we also have HSO4 minus. Let's see if HSO4 minus acts as both an acid and a base in these reactions. So in reaction B, it accepts a proton to become H2SO4 minus. So if it accepts, then it is a base in reaction B. Okay, and then in reaction C, it donates to become SO4 minus. So it is an acid in reaction C, I meant. So it is acting as both an acid and a base. And then 4.1.3, the answer is therefore HSO4 minus, because clearly in B it is acting as a base, and then in C it is acting as an acid. Okay, and then 4.1.4, a conjugate acid base pair in reaction C. Okay, so reaction C, HSO4 minus, it's our acid. It donates it donates a proton to become it donates a proton to become SO4 to the 2 minus. And then we know that a conjugate base, it's what's left after an acid donates a proton. So the pair HSO4 minus and SO4 2 minus. So there we go. That is 4.1.4. Okay, 4.2, grade 11 learners uses 2 steps to react sodium carbonate with concentrated sulfuric acid. In step 1, they prepare 250 centimeter cube standard solution by dissolving 5.13 grams of Na2CO3 crystals in distilled water. They reacted the prepared Na2CO3 with H2SO4. Okay, right. The reaction occurs according to the following balanced equation. And then 4.2.1, define an acid according to Arrhenius theory. Right, we're getting tired of these definitions. I think we have defined an acid and a base as according to Arrhenius theories and Brønsted theories. in these questions collectively. We have defined everything, I think. So an acid is a substance that ionizes to produce hydrogen ions when dissolved in water. That is 4.2.1. So 4.2.2, calculate the concentration of Na2CO3 in the standard solution. Okay, right. Let's take a look at the information that we have, because physics, well, physical sciences, is just a matter of, you're given information, you have a principle, and you use the principle to find the unknown using the information that we have. So here, the concentration is our unknown. We're trying to figure out what the concentration is. And then what information do we have with regards to Na2CO3? Okay. We know that we have a mass of 5.13 grams that is dissolved in distilled water. So the mass is equals to 5.13 grams. And then the volume of the distilled water, right? Because we have some water here and we are adding Na2CO3. The volume of the water is 250 centimeter cube. Okay, so concentration is equals to number of moles divided by volume. So we have the volume, we don't have the number of moles, but we can find the number of moles using the mass, right? Number of moles is equals to the mass divided by the molar mass. Okay, so concentration is equals to, in place of number of moles, mass divided by molar, we divide everything by V. This is just equals to the mass divided by the molar mass multiplied by the volume. So we can just use this equation to find the concentration of Na2CO3. So what is the mass? The mass is 5.13. Okay, and then the molar mass is sodium is 23, so we have 23 multiplied by 2, and then carbon is 12, oxygen is 16. You multiply by 3, you multiply that by 3, and we get 106 multiplied by the volume, which will be 250 times 10 to the minus 3. We are converting it to decimeter cube by doing that. So 106 multiplied by 0.25. Right, let me see what I get there. I'm getting 0.2 moles per decimeter cube. That is the concentration of Na2CO3, 4.2.2. What about 4.2.3? We're looking for the number of moles of H2SO4 that reacted. The number of moles of H2SO4 that reacted. Okay, we're looking for the number of moles of H2SO4. We're looking for the number of moles of H2SO4. What can we use? We can use the number of moles of Na2CO3 and the balancing coefficients of the two. Because take a look at this. The number of moles of Na2CO3 is 2. The number of moles of H2SO4 should be 1:1 because of the balancing coefficient. So we just need to figure out what the number of moles of Na2CO3 is, and then we have the number of moles of H2SO4 that reacted. Take a look at this. At this point, we have the concentration of Na2CO3, and we also have the volume. So finding the number of moles should not be that difficult. So the number of moles of H2SO4, we now know that it is equals to the number of moles of Na2CO3 will be equals to the concentration of Na2CO3 multiplied by the volume of Na2CO3, right? Okay, because we have established this relationship, we are then able to do this, right? So before you establish this relationship, you can't do this. So the concentration 0.2, the volume 250 divided by 1000. So let me just put that in my calculator and see what I get. I'm getting 0.05 moles. So we have two beakers A and B containing strong bases. Beaker A has 500 centimeter cube of BaOH2, and then of unknown concentration. And then beaker B has 400 centimeter cube of potassium hydroxide, KOH, of concentration 0.1 mole per decimeter cube. And then 7.1 says define a base according to Arrhenius theory. A base, according to Arrhenius theory, ionizes to form hydroxide ions. So that's basically the definition of a base according to Arrhenius theory. A base ionizes to form hydroxide ions. And then 7.2 says calculate the number of moles of hydroxide ions in beaker B. So what makes up beaker B? In beaker B, we are told that in beaker B we have KOH, right? And then when this ionizes, it will give you K plus OH minus, right? We are given information about KOH. So from the information we have about KOH, we'll then be able to find the number of moles of OH. So let's go ahead and do that. So we are told that the concentration is equal to 0.1 moles per decimeter cube. And then at the volume, it is given as 400 centimeter cube, which we have to convert to decimeter cube, right? We divide by 1,000, so we're gonna get 0.4 decimeter cube. Now we can find the moles of KOH and then use that to find the moles of OH using the balancing coefficients. So we're gonna get N of KOH is equals to C multiplied by V, right? We're saying that because we know that the concentration is equal to the number of moles divided by the volume. So we're using that formula. So N of KOH will be equals to, what is the concentration? 0.1 mole per decimeter cube. And what's the volume? 0.4 decimeter cube. This will give us 0.04 moles, right? And then now we can use this number of moles of KOH to determine the number of moles of OH minus, right? So we're gonna say the number of moles of KOH divided by the number of moles of OH minus is equals to 1 divided by 1, because that's the balancing coefficients. So basically the number of moles of OH minus is just equals to the number of moles of KOH, which is equals to 0.04 moles. And that's how you do 7.2. And then moving ahead, we have 7.3, which says the contents of beakers A and B are added together in beaker C. The solution is in beaker C has a pH of 13. So we have pH equals 13. And then from pH, before we go any further, we can determine the pOH, right? Because we know that pH plus pOH equals to 14. So that will say pOH equals to 14 minus 13. So pOH is equals to 1. Okay, let's move forward. So it goes on to say that assume that the volumes are additive and that the temperature of the solution is 25 degrees Celsius. And then 7.3.1 says calculate the concentration X of the BaOH2 in beaker A. So what is happening? Beaker A is being poured to beaker C, right? And then beaker B is being poured to beaker C. So beaker A has its own number of moles of OH, right? That will be poured to beaker C. And then beaker B also has its own number of moles that are going to be poured to beaker C. And then the number of moles in beaker A are unknown, but the number of moles on beaker N and in beaker B are known. And then we can use the pH to find the number of moles of OH minus in beaker C. So what we're going to do, we're going to find the number of moles of OH in beaker C. And then after that, we'll subtract the number of moles in beaker B. And then what will be left is the number of moles in beaker A. So if we go ahead and do that, let's find the number of moles in beaker C. So we have POH equals to 1. Like we determined above, right? And then we know that to calculate POH, we use the concentration of OH minus. So we're going to have minus log OH minus equals to 1. So we're going to have log OH minus equals to minus 1. And now to solve for OH, we can say OH minus is equals to 10 to the power minus 1. You can always do that. It always works. So if you take 10 to the power minus 1, you're going to get OH minus is equals to 0.1. So we have the concentration of OH minus in beaker C. Now we can find the number of moles, right? So the number of moles of OH minus will be equals to the concentration multiplied by the volume, right? What's the concentration? It's what we just determined is 0.1. And then what's the volume? The volume, it is said to be additive, right? So we're going to add the volume of beaker A and the volume of beaker B. So that will be 500 centimeter cube plus 400 centimeter cube divided by 1000. And then if I get this, I put this in my calculator, I'm getting 0.09 moles, right? So now we have the number of moles of beaker C, which is equal to the number of moles of beaker B plus the number of moles of beaker A. The number of moles of beaker C is 0.09. The number of moles of beaker B is what we calculated in 7.2, and that was I think 0.04, right? And then plus the number of moles of beaker A. So the number of moles of beaker A will be equal to 0.09 minus 0.04, which is equal to 0.05. So now we have the number of moles in beaker A. So we can use that to calculate the number of moles of BaOH2. So BaOH2, when it ionizes, it becomes Ba plus 2OH, right? So we can see that the balancing coefficient is 1:2. So we're going to have the number of moles of BaOH2 divided by the number of moles of OH being equals to 1 divided by 2, right? So we're going to have the number of moles of BaOH2 equals to the number of moles of OH divided by 2. So that is equal to 0.05 divided by 2. If I put that in my calculator, I get 0.025. So now we have the number of moles of BaOH2. We can then calculate the concentration. We know that concentration equals to number of moles divided by V, right? The volume. The number of moles is 0.025, and the volume is the volume of beaker A, not beaker A and B added together. So we're gonna have 500 divided by 1000. And then if you put this in your calculator, you're gonna get 0.05 mole divided by decimeter cube, which is equals to X. And then we can move forward. 7.3.2, it starts with the statement there that says the solution in beaker C is titrate. The solution in beaker C is titrated with ethanoic acid. It was found the solution in beaker C is titrated with ethanoic acid. It was found that 15 centimeter cube of the solution neutralizes 30 centimeter cube of the acid, and then we are given a balanced equation. And then 7.3.2 says, is ethanoic acid a weak acid or a strong acid? At this point of time, you should know that ethanoic acid it's a weak acid. And then it says give a reason for the answer. In grade 12, you will only provide one reason for why an acid is weak. That is to say, it ionizes incompletely. And then 7.3.3 says calculate the concentration of the ethanoic acid, right? So they neutralized completely. So let me write the equation again. So we have CH3COOH plus OH minus, which is giving us CH3COO minus plus H2O. So again, we can use the number of moles of one to find the number of moles of the other. If you pay careful attention, when you are doing problems in chemical equilibrium and acid and base, you always relating the number of moles, right? You start with one and then you try to figure out the other and vice versa. So we have information for OH, which we can use to determine the concentration of the ethanoic acid. So we determine the concentration of OH minus in 7.3.1, right? And it was 0.1 moles per decimeter cube. And then we're given the volume to be 15 centimeter cube, which we'll have to convert to decimeter cube. So the number of moles from this will be given by the number of moles equals to the concentration multiplied by the volume, right? The concentration is 0.1 and then the volume is given as 15 centimeter cube. So that will be 0.1 multiplied by 15 divided by 1,000. We divided it by 1,000 because we convert it into decimeter cube. That will give us 0.0015 moles, right? We can see the balancing coefficient that this is 1 and this is 1, right? So the number of moles of OH equals to the number of moles of our ethanoic acid. So to calculate the concentration of ethanoic acid, we're going to say concentration equals to number of moles divided by volume. And then we know that the number of moles is the same as the number of moles of OH because the balancing coefficients are the same, right? So we're going to have 0.0015. And then what is the volume? The volume is given as 30 centimeter cube. So we're going to have 30 divided by 1,000. Which is going to give us, let me put that in my calculator real quick. So we have 0.0015 divided by 30 divided by 1000. That is equal to 0.05 moles per decimeter cube. And then you get your 18 marks. Two reactions of sulfuric acid are shown in the diagram below. And then the first question, which is 8.1.1, says define a Lowry Brønsted base, right? This is the guy or the girl, not really sure, that defines a base and an acid the easy way, right? An acid, it's a proton donor, and then a base is a proton acceptor, right? So 8.1.1 proton acceptor, and you get 2 marks. And then 8.1.2 says write down a balance equation for reaction 1. Let's take our attention to reaction 1. So reaction 1, we have sulfuric acid H2SO4 and NaOH. So we have an acid plus a base, right? And an acid and plus a base. An acid and a base will always give you a salt plus H2O, right? That's just the general idea when you have an acid and a base. So we have H2SO4 plus NaOH, and this will give us something, right? Let me put the arrow here for the sake of space. So we need the acid to donate protons, right? And then we need the base to accept. So when the acid donates, we're going to have this H2O here from the general formula, right? So we're going to have H2O. So if we have H2O on the acid, we're going to be left with SO4. So this Na, which was accompanying the OH, which turned to H2O, will be here with NaSO4, right? It will be our salt. But then I want you to realize something. Since H2SO4 lost 2 hydrogens, it will now be SO4 2 minus, right? And then we know that Na is only plus. So we're gonna need 2 NAs. So we're gonna have Na2SO4 plus H2O. Now, when we're at this point, we can then balance our equation. So we have 2 hydrogens here, we have 1 here, and then here we have 2. So the hydrogens are not balanced. How can you possibly balance this hydrogen? If we put a coefficient of 2 here, we're going to have 4 on the right, and we're going to have 3 on the left. But if we put a coefficient of 2 here, then we have 4 on the left and 4 on the right. So now the hydrogens are balanced. We can look at S. We have 1 S here, we have 1 S here, so that is balanced. And then let's look at the oxygens. We have 6 oxygens on the left hand side, and then on the right hand side we also have 6 oxygen. So it seems like all is well, and we can move to 8.1.3. But for the most part, there's only a few reactions you're gonna be examined on, right? So just go to your exam guideline, go through past exam papers, and just memorize all the reactions that you see. And then 8.1.3 says, write down the name of the salt represented by X. So the salt represented by X is Na2SO4. What is Na? We know that Na is sodium, and SO4 is sulfate, right? And that is exactly what the name of our compound is. The name of our salt is sodium sulfate, right? But then it's not all the time that you just take the names of the different elements and then you just call it that. And then 8.1.4 says, let's write down the formula of ampholyte A. Ampholyte A is in our reaction 2, right? So in our reaction 2, we have H2SO4 plus H2O. And then it gives us, we know we're supposed to have H3O plus. So the sulfuric acid only donated 1 proton, right? So here we are left with HSO4 minus, right? So the name of our ampholyte is HSO4 minus. But is HSO4 minus an ampholyte? Yes, it is indeed an ampholyte. In this reaction, is acting as a conjugate base, right? But then if you say HSO4 minus plus H2O, then it's going to act as an acid. And then let's move to 8.1.5. Write down the formula of the 2 conjugate acid base pairs in reaction 2. So we've already written down reaction 2, right? Let's just look for the acid base conjugate pairs. So H2SO4 is an acid, and then when it loses the protons, we get the conjugate base, right? So if this pair is acid and base, then the other pair by default it will be our acid and base. So we can say H2SO4 and HSO4 minus is an acid base conjugate pair, and then H2O and H3O plus is another acid base conjugate pair. So whatever remains when an acid has donated a proton is the conjugate base, right? That's the rule of thumb. Now let's move to 8.2. 8.2 says a solution of sodium hydroxide NaOH is prepared by dissolving 6 grams solid NaOH in 500 centimeter cube of water. This solution reacts completely with 10 grams of impure ammonium chloride, NH4Cl, according to the equation below. And there we have our equation, and it says calculate the concentration of NaOH. So 8.2.1 NaOH. Problem solving 101. We have to write down the information we know about the NaOH, right? So we know fully well that the mass is 6 grams, and then the volume is 500 centimeter cube, and we want to find the concentration. Concentration is number of moles divided by the volume. So from the mass we can find the number of moles, and then we have the volume here. So let's go ahead and do that. So the number of moles will be equals to the mass divided by the molar mass. The mass is 6 grams, and the molar mass of NaOH is 40. So we're gonna have 0.15 moles, right? Now we can say that the concentration is equal to the number of moles divided by the volume, 0.15 divided by 500 centimeter cube, which you're gonna divide by 1000 to convert to decimeter cube. So we get in concentration of 0.3 moles per decimeter cube. And now we can move to the second question, which says let's calculate the percentage impurities in the NH4Cl. So let's break down percentage impurities. So we usually calculate percentage purity, right? So I'm assuming that percentage purity plus percentage impurity should be equal to 100%, right? So we can basically find the percentage purity, and then from the percentage purity, we're going to say 100 minus percentage purity is percentage impurity. Let me show you what I'm talking about. So we have 8.2.2. So we know that when we want to find percentage purity, we will need the mass, right? So let's say NH4Cl. So at the end of the day, we're going to need the mass, right? We know that initially the mass or mass total is 10 grams, right? We're going to find the mass. For purity, we will find the mass of the pure substance. So the mass that reacted, right? So let's go ahead and do that. What information do we have? Let's write our equation. NaOH plus NH4Cl is giving us NaCl and so on, right? So from the NaOH, we know that the concentration is equal to 0.3 moles per decimeter cube, and then the number of moles is 0.15 moles. And then we're supposed to use this information to ultimately find the mass of NH4Cl, right? Because there's no way we can find the percentage purity without knowing the mass. So how are we going to do that? We are definitely going to use the mole ratios of the two, right? Because in chemistry, for the most part, you're finding the number of moles and using it to find other quantities. So we can say that the number of moles of NaOH divided by the number of moles of NH4Cl will be equals to the balancing coefficient of NaOH is 1 and NH4Cl is 1. So now we're going to cross multiply. The number of moles of NH4Cl will be equals to 0.15 moles. The number of moles of NaOH multiplied by 1. So now we have the number of moles of NaOH. We can then find the mass of the NH4Cl that reacted, right? So the mass is given by the number of moles multiplied by the molar mass. We know fully well that the number of moles is 0.15, and then now we want the molar mass of NH4Cl. I think it is 53.5, right? So we get a mass of 8.025 grams. right? So 8.025 grams, it's pure, and then the remainder is impure, right? So we want to find the percentage impurity, not the percentage purity, right? So we know fully well that percentage purity is equals to mass of pure divided by mass of the entire sample, right? Multiply by 100. So percentage impurity will be equals to the mass of the impure, right? Divided by mass of sample multiplied by 100. It's a bit of, a trick equation, but not that much. So the mass of the impure, we're saying that initially we had 10 and 8.025 reacted, and then divided by the mass of the pure, which is 10 multiplied by 100, right? And that is 19.75%. You can do it even the other way that I suggested. You can find the percentage purity. So when you find the percentage purity, it will be 80.25%, right? So you would say 100 minus this value here, and you will still get 19.75%. So if you want the definition for 1 mole of a substance, then I've written it down in 6.1.1, right? You can just pause the video and copy it down. So what we're going to start with here is balancing the equation between sodium carbonate and hydrochloric acid, right? The equation is already given to us, but it's unbalanced, right? So that makes our job a little bit more easy. So let's go ahead and try and balance our equation. So on the left hand side, we have 2 atoms of Na, right? And then on the right hand side, we only have 1. So that means that the number of atoms of Na are not balanced. But how can we balance that? If we put a coefficient of 2 here, then we're going to have 2 atoms of Na on both sides, right? So now we can move from Na and go to carbon. On the left hand side, we have 1 carbon atom, and then on the right hand side we also have 1 carbon atom. So the carbon atoms are already balanced. We can move to the oxygen, right? Here we have 3 oxygen atoms, and then on the right hand side we have 1 here and 2 here. So we have 3 oxygen atoms on the left and the right hand side. So the oxygen atoms are balanced. Let's go to the hydrogens. Here we have 1 hydrogen on the left hand side, and then on the right hand side we have 2 hydrogens. We have H2, right? So the hydrogens are not balanced. How can we balance them? If we put a coefficient of 2 on the left hand side, then we're gonna have 2 hydrogens on the left hand side and 2 hydrogens on the right hand side. Now let's look at Cl, right? We have 2 atoms of Cl on the left hand side. On the right hand side, because of this coefficient 2 that we use to balance Na, we also have 2 Cl, right? So now our equation is balanced. We only had to add 2 here on HCl and 2 on NaCl. Let's do 6.1.3. So 6.1.3 says calculate the mass of sodium carbonate that reacted, and then there's 7 marks. In order to do these questions, you have to be extremely sober. There's no other way around it, right? You have to be, extremely sober. So let's look at our statement, right? We are told that in an experiment, a learner added 1.5 grams of sodium carbonate, right, to hydrochloric acid. A volume of 306 centimeter cube of carbon dioxide was formed and collected under standard pressure at room temperature. Take the molar gas volume at room temperature as 24.45 decimeter cube, right? So let me just copy down the equation again real quick, because we have to use this equation, right? If we don't have the equation and we just writing things, then it becomes all over the show, right? There need to be clarity in our writing, right? So we are told that at the end of the day, we have a volume of 306 centimeter cube of CO2 produced. And for the sodium carbonate, we are given an initial mass, which is 1.5 grams, right? So of this 1.5 grams, not all of it reacted, right? That's why the question is asking us to calculate the mass that reacted. But how can we calculate the mass that reacted? Using the CO2, right? The volume of CO2 that was produced, we can find the number of moles of CO2 that we produce. And then with the number of moles of CO2 that we produce, we're gonna then use the mole ratio to find the number of moles of Na2CO3 that reacted. And from the number of moles, we can find the mass. Let me show you what I'm talking about. Let's not forget that here we have the balancing coefficients. So the number of moles of CO2, we're going to have the number of moles being equals to the volume divided by molar gas volume, right? If you have a volume of a gas, that's how you can find the number of moles. You use this formula here. So what is the volume? We know fully well that the volume is 306 centimeter cube, right? But then in chemistry, we don't use centimeter cube, we use decimeter cube. So what do? We divide by 1,000 from centimeter to decimeter cube. So we're gonna say divided by 1,000, and then we divide by molar gas volume. Is given to us as 22.45 decimeter cube. And then if you punch that in your calculator, you're gonna get 0.0125 moles per decimeter cube, right? So now we have the number of moles of CO2 that were formed with part of the sodium carbonate that reacted. Now using the mole ratio, we're going to be able to find the moles of Na2CO3 that reacted, and consequently the mass that reacted, right? So now we can say the number of moles of CO2 divided by the number of moles of Na2CO3 is equals to the balancing coefficient. What is the balancing coefficient on CO2? The balancing coefficient is 1, right? And then the balancing coefficient of Na2CO3 is also 1. Yeah, if you're still so confused and you don't even know what a balancing coefficient is this number here, right? You can see for NaCl the number is 2, for HCl the number is 2, for Na2CO3 we don't have anything, right? But we actually have, it's 1, right? And then for CO2 it's also 1. Just in case. So now we can say that the number of moles of Na2CO3 will be equals to, we cross multiplying with multiplying everything by 1, right? So it will just remain how it is. It's equals to the number of moles of CO2 being equals to 0.0125 moles per decimeter cube. So now we have the number of moles of Na2CO3 that reacted, and we can then find the mass, right? Because we know fully well that the number of moles is equals to the mass divided by the molar mass if you're dealing with a solid, right? So now we can say that this is for Na2CO3. Let's not forget that. So now we can say that the mass is equals to the number of moles divided by the molar mass. We cross multiply, right? So we're going to have 0.0125 multiplied by the molar mass of Na2CO3. It's 106. You can verify that on your periodic table, right? And then the answer we get in now is 1.33 grams, right? So that's the mass of Na2CO3 that reacted, right? Let's do 6.1.4. Calculate the percentage of sodium carbonate in excess. So we have the mass that reacted, right? We have the mass initial that we started with, right? So we can find the mass in excess, right? Because let's say for Adam and Eve's sake, right? You have initially you had 5 apples, and then something happens to your apple, and then after, right, in excess, basically you have 2 apples. How many apples were used? You would say 3, right? So this is just telling us that the mass that is used is equals to the mass initial minus the mass in excess, right? You cannot deny for Adam and Eve's sake. So the mass initial is given to us as 1.5, right? The mass in excess, that's what we're looking for, mass in excess, right? And then the mass used is what we calculated here, right? We have 1.33. So now you're going to take this term to the left hand side, right? You're going to have 1.33 minus 1.5, right? And you're going to get minus 0.17 being equals to minus the mass in excess, right? It's easy, divide both sides by -1, and then the mass in excess is equals to 0.17 grams, right? So now we can say that the percentage of CaCO3 in excess, right, will be equals to, so we have 0.17 divided by the initial mass, which is 1.5, multiplied by 100. Obviously, we want the percentage. So that will be 11.33 recurring, right? And so on, percent. You can see here the kind of stuff we do in that you have no choice. You have to be, extremely sober, right? Let's do 6.2. 6.2 is saying that zinc reacts with sulfuric acid according to the reaction below, right? And then there we have our reaction. The mass of zinc is recorded during the experiment and is shown on the graph below. The reaction stops after 2 minutes, right? So let's analyze our graph for just a second. Initially we had a mass of 5 grams, right, at t is equals to 0, and then after some time the mass is now 2 grams and it stays at 2 grams, right? And then 6.2.1 says name the substance that is the limiting reactant, right? Let's analyze our situation. We have zinc and sulfuric acid, right? The mass of zinc starts at 5 grams, right, here, and then at 2 grams it never goes down, it remains there. Clearly, what was causing the mass of zinc to be converted to something else is depleted, right? So zinc is being limited by something it's reacting with here, and the only thing it's reacting with is sulfuric acid, right? So the substance that is acting as the limiting reagent is the sulfuric acid, right? So 6.2.1, you just say sulfuric acid. And now we can do 6.2.2. 6.2.2 says calculate the initial concentration of the sulfuric acid if 50 centimeter cube of the acid was used. All the time when I have a question like this, I'm going to write the formula down, right? If I cannot see the formula on the answer sheet, it's just, too confusing for me. So I have the zinc plus H2SO4 giving me ZnSO4. I don't know what the name of that is, plus H2. Stories. The question is saying from the sulfuric acid, let's find the initial concentration, right? But because you are a chemist, we know that to find the concentration, we need the number of moles and the volume, right? But I kid you not, they've given us the volume here. So what we want is only the number of moles. We know that the volume is equals to 50 centimeter cube, right? Which we are obviously going to convert to decimeter cube. So we want the initial concentration. So we need the number of moles of H2SO4, right? the number of moles of H2SO4. How can we find that? We can use zinc, right? Because we know fully well the mass of zinc that reacted, right? Again, for Adam and Eve's sake, initially we had 5 grams of zinc, and then after some time we have 2 grams. So how much reacted? It should be clear to see that 3 grams of zinc reacted, right? So now we can say that with regards to zinc, we know that the mass that reacted is 3 grams, right? So from the mass, we can find the number of moles of zinc that reacted. And from the number of moles of zinc that reacted, we can use the mole ratio to find the number of moles of H2SO4. If we have the number of moles and we have the volume, we have the concentration, and we are done with our problem, right? So let me show you what I'm talking about. Now we say that the number of moles is equal to the mass divided by the molar. So what is the mass? The mass is 3, right? And the molar mass of zinc, that is 65. And when you punch that in your calculator, you should get 0.0462 moles, right? Again, the mole ratio. So the number of moles of Zn divided by the number of moles of H2SO4 should be equals to the ratio of the balancing coefficients. So we have 1 divided by 1, right? So the number of moles of H2SO4 is equals to the number of moles of zinc, which is equals to 0.0462. I wish we had a problem where the balancing coefficients were not 1 and 1, because I feel like people will make mistakes, because in other questions you might not get 1:1. So make sure you go and watch other videos on acid and bases so that you can see how you manipulate this kind of equation when you don't have a balancing coefficient of 1 and 1, right? But yeah, stories. So now the number of moles of H2SO4 is that, right? And then now we can find the concentration. That's what the question is asking us to do. Concentration is equals to number of moles divided by volume. So we have 0.0462 divided by the volume, right? 50 centimeter cube. Obviously, we're going to divide it by 1,000. We deal with decimeter cube. We are chemists, right? And when you punch that in your calculator, I wish you get 0.92 moles per decimeter cube. 7.1.1. Is ethanoic acid a weak acid or a strong acid? Give a reason for the answer, right? So I'm gonna say it's a weak acid, right? Why am I saying it's a weak acid? I'm saying it's a weak acid because it's an ingredient of household vinegar, which you've probably used at some point of time. And if you pour a bit on yourself, you don't get burnt in any way. So it's a weak acid, right? But then when they say give a reason, they don't want you to say that. They now want the technical reason why it's considered a weak acid. So what is the technical reason? It's considered a weak acid because it dissociates partially in water, right? That's the reason they're looking for. So you're gonna say dissociates partially in water. And then we have 7.1.2. It says an ethanoic acid solution has a pH of 3.85 at 25 degrees Celsius. Calculate the concentration of the hydronium ions H3O plus in the solution. So fine, we know that pH is equals to minus log and then H3O plus, and then the pH is given to us as 3.85. So 3.85 will be equals to minus log concentration of H3O plus, and then we multiply everything by minus 1, right? So we're gonna get minus 3.85 equals to log HO3 plus, And then we can say that the concentration of H3O plus is equals to 10 to the power minus 3,85. And then if I put that in my calculator, I'm getting 1.41 times 10 to the minus 4 moles per decimeter cube. And then we have 7.1.3, which says sodium ethanoate CH3COONA, right, forms when ethanoic acid reacts with sodium hydroxide. And then it says, will the pH of sodium ethanoate solution be greater than 7, less than 7, or equal to 7? It's definitely gonna be greater than 7. Why is it greater than 7? We know now that ethanoic is a weak acid, right? So we have a weak acid being combined with a strong base, because sodium hydroxide is a strong base, right? So if you combine these two, you're gonna get a base, right? You will have a pH of greater than 7. So if instead you had a strong acid and a weak base, then the pH would be less than 7. And then we have 7.1.4, which says explain the answer to question 7.13 with the aid of a balanced chemical equation. So let's put sodium ethanoate in water and see what happens. So we have CH3 COONA plus H2O, and then this is supposed to give us something, right? So because we're saying that this is a base, right, because it has a pH of greater than 7, so this has to be an acid. So a base will accept a proton, right? And then the acid will donate a proton consequently. So if CH3COONA accepts a proton, we're gonna have CH3COOH plus NaOH. So we can see that we have hydroxide here, and as a consequence, the pH will be basic. So let's move forward and go to 7.2. 7.2 says household vinegar contains 4.52% of ethanoic acid, CH3COOH by volume, right? And then 1.2 gram of impure sample of calcium carbonate is added to 25 centimeter cube of household vinegar. On completion of the reaction, the excess ethanoic acid in the household vinegar is neutralized by 14.5 centimeter cube of a sodium hydroxide solution of concentration 1 mole decimeter cube. And then we have a balanced equation for the reaction. That's a mouthful, but let's see what we can do. So we have 7.2.1 saying calculate the number of moles of the unreacted ethanoic acid. So it is said that the excess ethanoic acid is neutralized by sodium hydroxide, right? So we're gonna have NaOH. This NaOH neutralize the ethanoic acid. But then we are told that the volume that does the neutralization is 14.5 centimeter cube, and then the concentration was 1 mole decimeter cube per decimeter cube, right? So what we can do, we can find the number of moles of NaOH related to the number of moles of ethanoic acid, and we're basically done, right? So from here we can see that the number of moles is equal to the concentration multiplied by the volume. We know the concentration fully well, that is 1, and the volume is 14.5 divided by 1,000. By now you should know why I'm dividing by 1,000. I'm converting the centimeter cube to decimeter cube. So if I divide that by 1,000, it's giving me 0.0145 moles, right? So now I want you to look at something. The balancing coefficient of our ethanoic acid is 1, and the balancing coefficient of our NOH is 1. So the number of moles of NaOH is equal to the number of moles of CH3COOH, and then that will be 0.0145 moles. But what if the balancing coefficients were not the same? I've solved a similar problem with that kind of situation, so I would advise you to go and check it out. So moving forward, we have 7.2.2, which says calcium carbonate reacts with the ethanoic acid according to the following balance equation, right? And then it says calculate the percentage of calcium carbonate in the impure sample if 1 centimeter cube of household vinegar has a mass of 1 gram. So what this question basically wants us to do is calculate the percentage purity of calcium carbonate, right? And then when we calculate in percentage purity, we'll always end up saying the percentage of the whatsoever we have, right, is equal to the pure divided by the impure and multiplied by 100. We have the pure, it's 1.2 gram is given to us, and now what we need to determine is the pure, right? But then how would we go ahead and do that? We need to find the number of moles of ethanoic acid that reacted, and by using that we can then relate the number of moles using the balancing coefficients, and consequently found the mass of the calcium carbonate. So for the number of moles of ethanoic acid that reacted, we still need the mass initial, and to determine that we're gonna say that the mass is equals to 4.52 divided by 100 multiplied by 25. Why am I saying that this will give us the mass? Because usually the mass is the number of moles by the molar mass. So look at this. This is the percentage of ethanoic acid in household vinegar, right? And then we are told in the equation that 1 centimeter cube, we can take it as 1 gram, right? So that's exactly what I'm doing there. So we're going to have 4.52 divided by 100 multiplied by 25, which is equals to 1.13 grams, right? And from this 1.13 grams, we can then calculate the number of moles of ethanoic acid initial, right? So we're gonna say the number of moles is equals to the mass, obviously, divided by the molar mass, which will be 1.13 divided by the molar mass of carbon is 12 plus 3 for the 3 hydrogens plus 32 for the oxygens plus 1, right? So let me punch this in my calculator real quick and see what I get. So divided by 12 plus 3 plus 32 plus 1 plus 12 again. I just missed the carbon there, and this is giving me 0.0188 moles, right? So now because we have number of moles in initial, right, and we have number of moles that are in excess, right, that didn't react, we can then calculate the number of moles that reacted. So we're gonna say number of moles that reacted equals to number of moles initial minus number of moles in excess, right? So the number of moles that reacted will be equal to the number of moles initial, which is 0.0188 minus number of moles in excess, which we calculated in 7.2.1, right? That is 0.0145, and then let me put that in my calculator real quick. That is 0.043. So now we can determine the mass of the calcium carbonate, right? So we can say that the number of moles of our acid divided by the number of moles of our base basically is equals to what the balancing coefficient of the acid is 2, right? And for the base is 1. So we're gonna say that the number of moles of the base equals to 0.043 divided by 2. If I do that, let me see what I get. It's giving me 0.00215. So from that 0.00215, we can calculate the mass of calcium carbonate, right? So we're gonna say that the mass is given by the number of moles multiplied by the molar mass. So this will be 0.00215. And what's the molar mass of calcium? Calcium carbonate. That's 100, right? Which is 0.215, right? So now we can come back to our formula for the percentage purity, right? And then for the impure, we can then put 1.2, and then for the pure, we can put 0.215. And then if we multiply that, we're gonna get about 18.08, right? Or something somewhere there. The following apparatus is used for the titration of a dilute alkali with a dilute acid. And we're given a balanced equation. And 7.1.1 says, what type of a reaction takes place when an acid is added to an alkali? An alkali is basically a base, right? So we have an acid and base reaction. So 7.1.1 acid and base reaction. Another name for an acid and a base reaction is neutralization, right? So you can write acid and base, or you can write neutralization. Now let's move to 7.1.2, which says that write down the name of the dilute alkali. So the acid is H2SO4, right? Which is basically sulfuric acid. Ba is barium, right? And then OH, you usually pronounce it as hydroxide, right? If you remember, if we have NaOH, this would be sodium hydroxide, right? So this will consequently be barium hydroxide. So here 7.1.2, we have barium hydroxide. 7.1.3 says, name the pieces of apparatus labeled X. So here's X here. You should be familiar with X at this point of time, right? X is a burette. It's essentially a glass tube, right? With readings on it, and it has a turning plug here, right? To control the amount you're putting in on your beaker or whatsoever you're using. So 7.1.3, we have a burette. And then 7.1.4 says methyl orange is used as an indicator. What will you observe in Y when the acid is added before the endpoint is reached? So before we add any acid, right, you are going to basically have a base, right? If you add methyl orange to a base, then the methyl orange is gonna turn yellow. So what we are going to observe between before the endpoint is reached is that the methyl orange turns yellow, and then as we add more acid, it will gradually turn to orange as we reach a pH of around 7. And then if you keep on adding more acid, and now the solution actually becomes acidic, then the methyl orange will turn red. So for 7.1.4, the methyl orange turns yellow because we add it into a base, and gradually turns orange. And if you keep adding more acid and your solution becomes acidic, it will consequently turn red. And then 7.1.5 says, state whether each of the following increases, decreases, or remains constant while the acid is being added before the endpoint is reached. So back to the basics. What's an acid? An acid is a proton donor. So when we increase the acid, we increase in H plus, right? So what will happen to Ba to the 2 plus, right? We won't have any effect on Ba to the 2 plus when we increase the acid, right? So Ba2 plus will remain constant, right? And then what will happen to OH minus? The concentration of OH minus will go down when we add H plus. Why am I saying that? So before we started adding the acid, right, we just had BaOH2 giving us Ba to the 2 plus 2OH minus, right? So when we add the acid H2SO4, the Ba2 plus will react with SO4 2 minus, and then the OH minus will react with 2H plus. So the more we add the acid, the more the concentration of OH minus decrease, right? Because OH plus H is clearly H2O. So here for OH minus is going to decrease. So for pH, we know that the pH is equals to minus log of H plus. The more you increase the concentration of H plus, the lower the pH will be, right? So as we increase H plus, the pH will consequently decrease. And then now we can do 7.1.6. 7.1.6 says that during the reaction, 50 centimeter cube of the dilute alkali reacts completely with 30 centimeter cube of the dilute acid. So the dilute alkali is reacting completely. That tells us that the dilute alkali is our limiting reactant, right? And then the question goes on to say, calculate the mass of barium sulfate that will form during the reaction if the concentration of the dilute alkali is 0.1 mole per decimeter cube. So we have the dilute alkali BaOH2, right? And then we are given the concentration. It is said to be 0.1 mole per decimeter cube, and then we are given the volume, which is said to be 50 centimeter cube. So if we find the number of moles of BaOH, then we're gonna be able to use those number of moles to find the number of moles of barium sulfate, right? And from the number of moles of barium sulfate, we'll consequently be able to find its mass, because that's what the question is asking us to do, right? So here we're gonna have the concentration is equal to the number of moles divided by the volume. If you make the number of moles a subject of the formula, you get concentration multiplied by volume. So what's the concentration? The concentration is 0.1, and what is the volume? The volume is 50 centimeter cube, right? But we'll deal with decimeter cube. So here we're going to have 50 divided by 1,000. So 50 divided by 1,000. So we basically have 5 divided by 1,000, which will be close to 0.005 moles, right? So if we go back to our equation again, the balancing coefficients, we have 1, 1, right? So the number of moles are basically equal for all those three that I just indicated there. So the number of moles of BaOH2 will be equal to the number of moles of BaSO4. So that will be 0.005 mole, right? Now we can calculate the mass of barium sulfate. We have the number of moles, and the molar mass we can get it from our periodic table. So now we know fully well that the number of moles is equal to the mass divided by the molar mass. If you make the mass of the subject to the formula, you get number of mole multiplied by the molar mass. So what is the number of mole? What we just calculated, right? So we have 0.005 multiplied by the molar mass of barium sulfate. If you add the molar mass of barium and SO4, that will give you 233. So 233 multiplied by 0.005, that is 1.165 grams. So the mass of the barium sulfate that will be formed will be 1.165 grams. I hope that is clear. Let's just recap for the last time. We're given the concentration and the volume of the dilute alkali or barium hydroxide, right, which was used, and then we figured out that it's our limiting reactant, right, because we are told that it reacts completely. So from there we find the number of moles of the alkali, the dilute alkali, and we use those number of moles to find the number of moles of the barium sulfate, right? And from the number of moles we calculate in the mass here, right? High school chemistry is basically finding the number of moles of one reactant and using it to find the number of moles of the other, and from there you'll find either the concentration or you'll find the mass. And then 7.2 says 2 test tubes contain solutions of NH4 NH4 I think, and CH3COONA. Their pH values are less than 7 and greater than 7 respectively. Write down the following rewrite the following hydrolysis equation in the answer book and complete them to explain this behavior. So for NH4+, we are told that the pH is less than 7, right? So if it is less than 7, it is acidic, and if it's acidic, then it's a proton donor, right? So that NH4+ is supposed to lose a proton, it's supposed to lose one hydrogen, right? So here we're gonna have NH3, right, instead of NH4, because now we have lost a hydrogen, plus H3O+, right? And then that's basically what you're being asked to do. And then now let's pay our attention to 7.2.2. It is said to have a pH of greater than 7. What does that tell us? It tells us that it is basic, so it's supposed to gain a proton, right? So we're gonna have CH3COOH, right? There we go, we have gained a proton, plus now the proton is coming from H2O, right? So the H2O now will be OH minus, and then now so the hydrogen that NH4+ lost came to H2O, right? So hence here we have H3O+.